Alright guys, hi, welcome to lesson 7. Whoop, whoop. Okay, so today we're going to start looking at something a little bit different from what we've been doing. Still on the theme of exponents, but now we're going to look at how do we figure out the power of a power and how do we simplify that? Okay, so last classes we were looking at how do we multiply um, powers that had similar bases, different exponents, or the same exponent didn't matter. Now we're going to have it all kind of in one, and what do we do? So 2 to the power of 3, all of that to the power of 2, right? We can again always do it step by step, but we're always in a mathematician mind of how can we do the least amount of work and simplify things to make the most sense. So that's what we're going to be working on today. Okay. So the first example here, we'll kind of do it the longer route, and then we're going to simplify things and look at how we can go about doing it in an easier way. All right. So here, this is the same thing as saying 3 to the power of 4, and then that times 2, so to the power of 8. Okay, and so that would equal 6,561. Okay, another way we could have done this problem is, well, what's 3 to the power of 4? Okay, so 3 to the power of 4 is equal to 81, right? And then all of that, right, because that was just what was in our brackets, to the power of 2, so squared, and that also equals 6,561, right? So this is kind of our proof that we can do it either approach, right, and it comes out to the same thing. So here, let's show it both ways again, just to make sure that we aren't cheating the system. All right, so we have 2 to the power of 3, that equals 8. And all of that to the power of 3, 8 to the power of 3, is 512. Okay. The other way we said we could look at this is if we multiply our powers, our exponents. Okay, so 2 to the power of 3 times 3, which is equal to 2 to the power of 9. Okay, and if we take our calculator, 2 to the power of 9, 2 to the power of 9 is equal to 512. Right? So this is kind of where we see both ways of doing it. And as mathematicians, the first time we always like to prove that our ideas work, right? So now that we've proven this, okay, we've shown you a couple of examples that show that we can just take our power to a power, and then we can multiply the exponents, right? So the way we can write that is x to the a to the power of b, the same thing as x to the a times b. So we get x, a, b, right? And this is kind of our variables because the numbers aren't always going to be to the power 3 or to the power 4 or power 2 or power 1,682, right? Those can change. So as long as we have our base as x and our exponents are a or b, whatever they might be, we can solve this. Okay, so here we're going to do a few more examples, just kind of show you how things are simplified, and then we'll get you guys doing some practice. Okay, so here we have 5 to the power of 3 to the power of 4, 3 times 4, 5 to the power of 12. Okay, here things get a little bit different, but it's still nothing crazy. We have in brackets -2, so it's all of this to the power of 10, all of that to the power of 5, so we end up with -2 to the power of 50. Okay, we don't need to evaluate or solve what this expression equals. That's just a lot of work. Okay, here we can go 3 to the power of 12 times 0, and sure enough, we know that any number times 0 is equal to 0, so 3 to the power of 0. You can't just leave it as 3, because we know that 3 to the power of 1 is equal to 3, 3 to the power of 0 is equal to 1. Keep that in your minds. Okay, next one up, we have -1 to the power of 3 times 5. Right, so then our solution would be negative 1 to the power of 15. Remember, if we are actually evaluating this, this negative is not included in what we're doing here. That comes after. Okay, so unless our bracket contains the negative is separate from the power. All right, don't forget that. All right, here we do have an example, right, where negative 1 is to the power of 3, and that to the power of 5. And you know that part where I just said we don't need to evaluate? Mr. B, read the full instructions all the way to the end. Apparently we do, so let's do that, okay? So we end up with negative 1 to the power of 15. Yeah, I'm going to do that in a different color just so we don't mix it up. But if we go here and we have 5 to the power of 12, oh, that is a big, big number. Not working there. Let's try there. All right. 4, 4, 1, 4, 0, 6, 2, 5. Okay. We have negative 2 to the power of 50. And that is equal to 1.13 times 10 to the power of 15. Too big to really solve. That's all right. We're going to talk about scientific notation. What does this mean in lesson, I believe it is 9. So we'll get there. Okay. Any number to the power of 1 is equal, or to the power of 0 is equal to 1. Over here we have 1 to the power of 15, which is 1. And this solution would equal negative 1 because it is powered. All of this also, because we have an odd number of negatives, it will also equal negative 1. Okay. Okay, let's keep it going. I'm going to go back to blue. Okay, so power over product. Here, again, we can always do what's in our brackets first and then go to the powers. So 3 times 4 is equal to 12, all of that to the power of 2. Okay, and we're going to kind of keep looking at a couple more solutions. Okay, so there's 2 different methods of solving. We could look at, all right, let's just make sure I get the right information for you guys. All right, so we can look at it as 14 to the power of 5, right, because 7 times 2 is to the power of 5. Or we can look at it as 7 to the power of 5 times 2 to the power of 5, right? So we can take this and add it to each of our bases within. Okay, so whichever one's simplified, we'll make this a little more clear as we go, but this is definitely an example of where we can do it, right? So here we have 2x to the power of 2, or we can look at it as 2 to the power of 2 times, right? That dot means times x to the power of 2. Sometimes it'll be easier to go this way, sometimes it'll be easier to go this way, especially when we start adding in variables to some of our problems. We're going to want to look at that. Okay, so here we can keep it as such, or we can go negative 3 in brackets because it's all contained, to the power of 3, times x to the power of 3 times y to the power of 3. Now we just keep this going. Okay, so here things get a little bit different, right? We have negative 4 to the power of 2 times, a to the power of 2 to the power of 2, so that's 2 times 2, okay? We have b to the power of 3 to the power of 2, so 3 times 2. We can simplify this as negative 4 to the power of 2 times a to the power of 4 times b to the power of 6. Okay, last example here, negative m to the power of 3 times m to the power of 3. Okay, so it's really just expanding things, simplifying things. Sometimes mathematicians like to oversimplify things so it fits on a nice sheet of paper, but then we need to re-expand if we actually want to do any math with it. Depends kind of what we're doing. Okay, so the power product rule is the general rule is a to the power of b, the power of m, is equal to a to the m times b to the m. Okay, and that's just showing how we can take this and apply it to both of our exponents. Oh, this is not a superscript, sorry. A times b. There we go. Sorry if you had to erase anything with your pencil. If you were using pen, well, we should always be using pencil with math, even in our notes. Okay, so we got a few examples of quotients, also known as divisions. And how do we look at that? Well, things don't really change too much here either. Okay. So here we have 4 divided by 2, all of that to the power of 3. Okay, so you can go and simplify it same way. 4 to the power of 3 divided by 2 to the power of 3, right? You can split that up amongst your things if you want to get rid of the power outside of the brackets. Over here, same thing applies. Okay, we can go all of this negative 2 to the power of 3 divided by 5 to the power of 3. And again, whether it's written as a fraction or in a single line, same things apply. So we can go 24 to the power of 2 divided by 3 to the power of 2. Right? So we can write this as a general rule of a over b. All of this to the power of m is equal to a to the m divided by b to the m. Okay, and it's really just showing how we can expand our problems. Okay, so why don't we put this all together and we'll look at a few more examples and then we'll kind of get going. Okay, I'm going to do it on a few separate sheets just because it's a lot of writing and I want to make sure that we have the space we need. Okay, so for problem 8, we'll start small and we'll grow big. Okay. The first thing we want to do is rewrite the problem, and there's no issue for me if you want to take it this, and there's not enough space where you're on a separate sheet of paper. I'd rather have that than you squishing everything in and not be able to read what you're doing. Okay. So 3 to the power of 2 times 3 to the power of 3, and all of this to the power of 3, minus 4 to the power of 3 minus 4 to the power of 2. All of this to the power of 2. Okay, so first thing we're going to do is take what we've got here, and we can again solve this a couple different ways. We can either take it all expanded or we can do what we have inside. I'm going to take what we have inside, simplify that, and then go to the power of a power. Okay, so 3 to the power of 2 times 3 to the power of 3 is the same thing as 3 to the power of 2 plus 3. All of this is still to the power of 3. All of that is negative. Here we have the same basis, so the exponents can add 3 plus 2, and again, all to the power of 2. Okay, so this simplifies to 3 to the power of 5 to the power of 3, 4 to the power of 5 to the power of 2. Now again, we can simplify this more. So 3 to the power of 5 times 3 minus 4 to the power of 5 times 2. 3 to the 15 minus 4 to the 10. And if we take this and expand it, we get some massive numbers. So we end up with 1, 4, 3, 4, 8, 9, 0, 7. If you want to use recall or store functions, so you don't have to write this all out every time. Okay, but when we're showing our examples, I do want us to write this out. Okay, 1, 0, 4, 8, 5, 7, 6, and all of this 1, 3, 3, 0, 0, 3, 3, 1. Okay, so you see how it's done in a few steps, but again, it's a simple enough process if we take it one step at a time. and really just think about, okay, what rules can I apply here with my exponents? That's really what this whole unit is about, is there are set rules, and how do I follow those rules? Okay, so we're gonna go to B, C, and then it's gonna be your turn to try this. Okay. So here we can go 6 times 7 is 42 to the power of 2 times. In our brackets, we can do 3 to the power of 8 minus 6 because we have division, same basis, right? And all this to the power of 3. 42 to the power of 2 is the same as 3 to the power of 2 to the power of 3. 42 squared, a weird little growth defect now, is the same thing as 3 to the power of 2 times 3. 42 to the 2 times 3 to the 6. And then we can take this just one step farther, and 42 to the power of 2. 1764 times 3 to the power of 6. It's 729 times 1764. 128 5956. So one thing I might suggest to you guys if you want to try is even with the practice problems, pause the video, see if you can solve it before I do, and then after you're finished, hit play, see how I do it, see if it's similar to what you've done. If it's very out to lunch, then maybe you might want to rethink of how you've been going through the notes or asking a few questions to clarify things, right? Okay, last example, and then we are done. Okay. So for C, we have a division problem, right? Quotients. 2 to the power of 4 minus 2 to the power of 3. This is equal. See, when we have straight lines that like to go down, when we have division problems like this that look like a fraction like to go across, because it just kind of keeps all the lines nice and smooth. All right, so here we have 2 powers multiplying same base, so we're going to take our exponents and we're going to add them. This is still a division problem, so here we have a subtraction. Can we take these and combine them? No, we can't. Only when we're multiplying or dividing common powers. So here we still have 2 to the power of 4 minus 2 to the power of 2. This is 4 to the power of 5 over 2 to the power of 2 minus 2 to the power of 2, and 4. All right, now I'll take this to a separate line. 4 to the power of 5 is 1024. 2 to the power of 4 is 16. 2 to the power of 2 is 4. Okay. So we end up with 1024 divided by 12. And all of this is 1024 divided by 12 gives us a bit of a decimal, so we get 85.3 repeat. Okay, so that's all I have for you guys today. Good luck. Hope this is making sense. And once again, if there's any questions you have, highlight them, put a star, something to remind yourself to come talk to me after you finish this video. Okay, have a good one.